3.10 Related rates. The outline of this video is as follows. We will begin with an introduction to related rates problems, where our goal is to find the rate of change of one quantity by relating it to other quantities whose rates of change we already know. This powerful application of the chain rule allows us to connect how different variables, like volume and radius, change with respect to time. After establishing the core method, we will work through a series of diverse examples to see this principle in action. We will calculate how fast the water level rises in a conical tank, determine the speed of a hot air balloon, and even analyze a police chase scenario. We will also look at a particle moving on a circle, the changing distance to an approaching jet, and the rate at which a weight is raised by a pulley. Each example will reinforce a systematic approach to solving these problems, showing you how to translate a real-world situation into a mathematical equation that you can solve. Let us begin by defining what a related rates problem is, as this is a powerful application of the chain rules. A related rates problem asks us to find how fast one quantity is changing by using the known rate of change of a different, but related, quantity. To make this concrete, imagine we are pumping air into a spherical balloon. We know the formula for its volume, V, is V equals 4/3 pi times r cubed, which connects the volume to the radius r. To find the relationship between their rates of change, we can differentiate both sides of this equation with respect to time. Using the chain rule, we find that dv dt equals 4 pi r squared times dr dt. This new equation is powerful because if we know how fast the volume is increasing, we can now calculate exactly how fast the radius is growing at any instant. The key idea is that differentiating a static formula with respect to time gives us a new formula that connects the rates of change. To solve any related rates problem systematically, I recommend a 6-step strategy that transforms a word problem into a clear calculation. First, we set up the problem by drawing a picture, labeling all quantities that change over time as variables, and writing down all the given numerical information, such as a known rate. Next, we find the core relationship by writing an equation, often from geometry, that connects our variables. For example, this might be the Pythagorean theorem or the volume formula for a sphere. The key calculus step is to differentiate this entire equation with respect to time, which introduces the rates we are interested in. A common pitfall is substituting a numerical value for a changing variable too early. Always differentiate before you substitute. The final step is to plug in the known values for the specific moment in question and solve for the rate you need to find. Following these steps in order provides a reliable path to the correct answer every time. Let us walk through our first related rates example, which involves water filling a conical tank. Our goal is to find how fast the water level is rising given the rate at which the volume is increasing. We know the volume is growing at 9 cubic feet per minute, and we want to find the rate of change of the water's depth when that depth is exactly 6 feet. The volume formula for a cone, V equals 1/3 times pi times x squared times y, initially involves two changing variables, the water's radius x and its depth y. The key step is to eliminate one of these. Using similar triangles based on the tank's fixed dimensions, we see the ratio of the radius x to the depth y is always 5/10, meaning x is always y/2. By substituting this into the volume formula, we get a much simpler equation relating only volume and depth. V equals pi/12 times y cubed. Now we have a direct relationship between the two quantities whose rates we need to connect. With our simplified volume equation, we can now solve for the unknown rate by differentiating with respect to time. Applying the chain rule to the equation V equals pi/12 times y cubed gives us a new equation relating the rates. dv dt equals pi/4 times y squared times dy dt. This is the most important step, because it connects the rate we know to the rate we want to find. Now, we can substitute the known values for the specific instant in question. The volume is changing at a rate of 9, and the water depth y is 6. This leads to the equation 9 equals 9 pi times dy dt. Solving for dy dt, we find it is equal to 1 over pi, which is about 0.32 feet per minute. The essential takeaway is to differentiate the general relationship first, and only then substitute the instantaneous values to find the unknown rate. Let us put our problem-solving strategy into action with a classic example. Finding the speed of a rising hot air balloon. The goal is to find how fast the balloon is rising by using the known rate at which its elevation angle is changing. First, we establish a geometric relationship that connects the balloon's height, which I will call y, to the elevation angle, which I will call u. Using the right triangle shown, we can write that the tangent of angle u is equal to the height y divided by the fixed distance of 150 meters. The next crucial step is to differentiate this entire equation with respect to time, which gives us a new equation relating their rates. dy dt equals 150 times the quantity secant squared of u, all times du dt. Finally, we evaluate this expression by plugging in the given angle of pi over 4 and its rate of change of 0.14 radians per minute. This calculation reveals the balloon is rising at exactly 42 meters per minute. The core idea is to find the static relationship first, then differentiate to link the rates. Here we have a classic related rates problem, where the changing distances between two vehicles form a right triangle. I will model the car's eastward path along the x-axis and the cruiser's southward path along the y-axis, with the intersection at the origin. The variables x and y represent the legs of the triangle, and the distance between the vehicles, ss, is the hypotenuse. We are given the rates of change for the cruiser's position and the distance s. It is important to see that dy dt is negative 60 miles per hour because the cruiser is moving toward the origin, so its y position is decreasing. The relationship connecting our variables is the Pythagorean theorem. S squared equals x squared plus y squared. By differentiating this equation with respect to time, we get a new equation that relates all the rates. Our goal is to use this derivative and the given values to solve for dx dt, which is the speed of the car. Now we can solve for the car's speed by plugging our known values into the differentiated equation. First, we need the distance, as, between the vehicles at this exact moment. Using the Pythagorean theorem with x equals 0.8 and y equals 0.6, we find that s is exactly 1 mile. Next, we substitute all our knowns into the equation, s times d. S over dt equals x times dx over dt plus y times dy over dt. This becomes 1 times 20 equals 0.8 times dx over dt, plus the quantity 0.6 times negative 60. This simplifies to 20 equals 0.8 times dx over dt minus 36. Finally, solving for our unknown rate, dx over dt, we find it is 56 divided by 0.8. This means, at the moment of measurement, the car is traveling at 70 miles per hour. Here we have a great related rates problem, where the connection between our variables comes from trigonometry. The setup involves a particle moving on a circle, and we want to find the speed of a point Q, which is created by a tangent line intersecting the x-axis. First, we calculate the rate of change for the angle u. Since the particle moves pi over 2 radians in 30 seconds, the rate du dt is negative pi radians per minute. It is negative because the angle shrinks as the particle moves clockwise. Next, we need an equation linking the position of Q, which is x, to the angle U. From the geometry of the diagram, we can see that x equals 10 times the secant of U. Differentiating this with respect to time gives us our related rates equation. dx dt equals 10 times the quantity secant U times tangent U, all multiplied by du dt. This gives us the general formula we need to solve the problem. Now that we have our derivative equation, we can find the speed of point Q at the specific moment when it is 20 meters from the origin. First, we use our geometric relationship, where x equals 10 times the secant of U, to find that the secant of U must be 2. Next, using a trigonometric identity, we find the tangent of U is the square root of the quantity 2 squared minus 1, which simplifies to the square root of 3. Finally, we substitute all our known values into the derivative equation. We have 10 times our secant of 2 times our tangent of the square root of 3, all multiplied by the angular rate of negative pi. This gives a final velocity of negative 20 times the square root of 3 times pi, which is approximately negative 109 meters per minute. The negative sign confirms that point Q is moving toward the origin. So at this exact moment, point Q is approaching the origin at about 109 meters per minute. Now let us apply our related rates method to a classic problem involving the speed of a jet airliner. We have an aircraft flying at a constant altitude of 12,000 feet, tracked by a radar station on an island. This setup forms a right triangle where the horizontal distance, which we call x, and the radar's angle of elevation, u, are both changing over time. To connect these variables, we can use trigonometry, finding that x equals the constant altitude times the cotangent of the angle u. By differentiating this entire relation with respect to time, we get a new equation that links the rate we want, dx divided by dt, to the rate we are given, du divided by dt. For this problem to work, we must be careful to convert all our units consistently, for example, changing feet to miles and degrees per second to radians per hour. This final differentiated equation allows us to calculate the plane's horizontal speed based on how fast the radar angle is changing. Now we can solve for the aircraft's speed by substituting our known values into the derivative equation we found. A crucial first step is to handle the units correctly. Because calculus with trigonometric functions requires radians, and we want a final speed in miles per hour, we must convert the angular rate. This changes 2/3 degrees per second into 40 pi over 3 radians per hour. Next, we evaluate the cosecant squared of our angle, pi over 6, which gives us a value of 4. We can now substitute both the converted rate and this value of 4 into our equation for the rate of change of x. This gives us the expression negative 12,000 over 5280 times 4 times the quantity 40 pi over 3, which calculates to approximately negative 380 miles per hour. Remember, the negative sign indicates the distance x is decreasing. The aircraft is therefore approaching the island at about 380 miles per hour. Let us apply our problem-solving strategy to this classic pulley system, where our main task is to find two separate equations that connect all the changing quantities. First, we define our variables. Let x be the worker's horizontal distance from the pulley's vertical line, h be the weight's height above the ground reference, and z be the length of rope from the pulley to the worker's hand. We can see a right triangle in the diagram, where the vertical side is a constant 20 feet. The Pythagorean theorem gives our first relation. 20 squared plus x squared equals z squared. Our second equation comes from the fixed total rope length of 45 feet. This length is the sum of two parts: the segment from the pulley to the hand, which is z, and the segment to the weight, which is 20 minus h. So the quantity 20 minus h plus z equals 45. We now have two equations linking our variables. which is the complete setup needed before we can differentiate. Now we can solve for the rate at which the weight is rising by connecting our two geometric relationships into one. I will first combine our equations to eliminate the rope length z, which gives us a single formula relating the horizontal distance x to the height, 20 squared plus x squared, equals the quantity 25 plus h squared. The next crucial step is to differentiate this entire equation with respect to time t. After applying the chain rule, I can rearrange the terms to solve for our target rate, dh over dt. Before substituting our known rates, we must find the value of the term 25 plus h at the specific instant when x is 21 feet. A quick calculation shows this value is 29. Finally, I can plug in all the knowns, which gives us the fraction 21 over 29, multiplied by 4. This means the weight is rising at approximately 2.9 feet per second at that moment. To wrap up, I will summarize our powerful, systematic method for solving related rates problems, where quantities change over time while being linked by an equation. The entire process hinges on 4 key steps. First, always begin by drawing a diagram to visualize the problem, naming all your variables and constants. Second, clearly identify the rates you are given and the specific rate you need to find. The third and most creative step is to write an equation, often from a geometric formula, that connects these variables. Finally, you apply the chain rule to differentiate your equation with respect to time, and only after differentiating do you substitute the known values to solve for your target rate. For example, the sphere's volume formula was all we needed to connect the inflation rate to the radius change. Following this structured approach is the key to successfully navigating these problems in physics, engineering, and beyond. To finish, let us explore a couple of questions that will help solidify our intuition about how these related rates behave. First, for the conical water tank, if the water level were to rise at a constant rate, would the rate of water being pumped in also be constant? The answer is no, because the rate of change of volume is proportional to the square of the water's depth. This means you would need to pump water in much faster when the tank is nearly full and wide, compared to when it is nearly empty and narrow. Second, in the police chase, if both vehicles traveled at 60 miles per hour, the distance between them would still be increasing, at that specific moment, the car is moving mostly away from the cruiser, while the cruiser's motion is nearly perpendicular to the line connecting them. The car's eastward speed separates them more than the cruiser's southward speed closes the gap, causing the distance to grow at 12 miles per hour. The key lesson is that our initial intuition can be misleading, so we must always rely on the derived rate equation to understand the full picture.